second lecture in Module 9 on numerical simulation of turbulent flow. So, in this module we had discussed the features of turbulent flow, what are the basic elements which differentiate the turbulent flows from laminar flows, and we also discussed briefly the numerical simulation strategies of turbulent flow and how different length scales and time scales which are present in turbulent flow make our life pretty difficult. So, we had a brief look at the main simulation strategies, and we had also had a look at the time cost of simulation if we just want to solve or simulate all length and time scales in a turbulent flow using the so called DNS or direct numerical simulation strategy. Now, next we are going to have a look at what we call a RANS turbulence model, and in the next lecture we would cover what we call large eddy simulation. So, let us have a recap of the previous lecture. We discussed the basic features of turbulent flow. Its dissipative nature is random fluctuations which form integral part of turbulent flow, its unsteadiness, three dimensionality, its diffusive nature and its dissipative nature. We also discussed the various other features, the length scales which are present, their rough estimation, and the numerical simulation strategies, namely the direct numerical simulation which would involve the resolution of all length and time scales requiring very fine grid, which makes DNS impractical for industrial flow simulations. And we also looked at the time scales which said, look, we can use DNS primarily for research purposes to understand the basics of fluid dynamics of the turbulent flows and to refine what we call the turbulence model used in RANS and large eddy simulation. We also briefly discussed the Reynolds proposition of what we call Reynolds decomposition, and that's where we are going to pick up from. We will start off our lecture on Reynolds averaging and a RANS simulation model. RANS stands for Reynolds averaged Navier-Stokes simulation, and RANS simulation models are the ones which are today the practical tool for industrial scale simulations. Only recently, with the advent of very high performance computers available with big corporations, that people have been trying to use large eddy simulation for final design comparisons. For the initial design and design iteration cycles, RANS is still what we can practically employ. So, we will have a look at some of the RANS models in this lecture. So, the outline of the lecture, we would first have a look at the so called Reynolds averaging procedure which is used in Reynolds decomposition. Then we would derive so called Reynolds averaged Navier-Stokes equations, in short they are called RANS equations, and we will look at few major turbulence models. Why do we need these models? That would become apparent when we have a look at our Reynolds averaged Navier-Stokes equations which have additional terms which must be modeled. And these turbulence models, they try to come up with some formulae for those unknown additional terms in terms of the primary quantities. Now, this is what we had discussed in the last lecture, the Reynolds decomposition. Osborne-Reynolds suggested that we had any flow variable phi in a turbulent flow field. It can be broken into two parts, one which can be attributed to the turbulent fluctuations which are random in nature, and if a flow were statistically stationary, other part could be what we call time averaged value. So, that is to say that for any variable phi we can write phi at a spatial location x and time instant t. It can be written as sum of two parts, phi bar x. Now, this particular part, the average part or mean value part, it is independent of time, it only depends on the spatial location, plus phi prime x comma t. So, phi prime x comma t, that represents randomly varying fluctuating components of the scalar phi. Now, this phi could be one of the velocity components, it could represent density in compressible flows and pressure or temperature. So, any flow variable which we encounter in turbulent flows might have or might be decomposed using this simple strategy in terms of its mean value and fluctuating components. Now, this specific region why we want it. In engineering flow simulations, we are interested in time averaged quantity. We are not interested in what happens to the flow variables at every spatial location at each instant of time. Doing that would be next to impossible for large scale industrial simulation. We are interested in average quantities, like we want to know the forces, drag, lift, the pressure drops occurring across, let's say, a length of a pipe or piping network, and so on. So, we are primarily interested in what we call the gross quantities or average quantities, and in fact, it does not make much sense for us to try and resolve all the length and time scales in our simulation. That is what we would attempt in direct numerical simulation. That would be a colossal waste of time. So, we would try to find out these time averaged quantities through our simulations, and in terms of these quantities we can calculate the values of engineering interest, that is to say the forces acting on the surfaces, that in terms of what we require as a net drag force or lift force or the pressure drop, energy loss, and so on. Now, we had used this word phi bar or average. How do we define these average terms? So, what Reynolds suggests is that if you are dealing with statistically steady turbulent flows, that is to say the flow rate remains constant with respect to time if you take the average over a fairly large time period. So, in that case, for such flows which are formally called statistically steady, Reynolds averaged is the time average, and we would define it as phi bar x is equal to limit capital T tending to infinity 1 by capital T 0 to T phi x t dt. Now, this capital T represents the averaging interval which must be large compared to the typical time scales of the fluctuations. Otherwise, we would not get the statistically averaged value of the scalar field phi at a spatial location x. But in case the flow were inherently unsteady, that is to say there were fluctuations, but even the average flow rate is varying with time. So, suppose we have taken a pipe flow and we are steadily increasing the flow rate through the pipe network. So, the flow rate even in average sense, that is varying or changing with time. So, in such situations we cannot use a time average. So, we have to define a different averaging procedure, and now in this case our phi bar will not be just a function of this spatial location x, it will also depend on time, and we would define it using what we call ensemble average. So, ensemble average is defined in terms of what we call identical experiments. If we had an opportunity to perform the experiments in identical conditions, and each time we measure our variable phi at different locations in time. So, at a given location at a given time, let us take out n number of measurements and let us take average of those n number of measurements. So, each phi n x t, that represents one sample or one measurement. We have taken capital N number of measurements, take their average, and this n, capital N, should be fairly large number to give us what we call ensemble average. And this phi bar x t would be now the unsteady average terms, and the related RANS equations, what we call those are called unsteady RANS. But most of the time you would be dealing with the time averaging. And if you look at the two definitions, that is one which we had in the previous slide, which is defined in terms of an integral of the quantity phi x t over time, or in terms of this summation, both of them are basically linear operations. So, there are certain consequences of this linearity. Okay, so, the Reynolds decomposition which we had, that was defined as sum of two quantities, that is a linear operator. Similarly, the averages which we defined, those were defined in terms of linear operators. Integral again is essentially, it can be represented as summation, which is a linear operator. Similarly, in ensemble average we had a simple summation. So, that is again a linear operator, and there are certain algebraic rules which we can formulate for algebra of averages and fluctuations of any two flow variables phi and psi. The way we had defined our time averaged values, so if you take our Reynolds decomposition, if you want to find out the average of the fluctuation, what do we get? Now let us briefly have a look at whether this particular thing, are we satisfied with this 5-hour average would be 0. So remember, we have defined our decomposition as phi x t. This was defined as phi bar x plus phi prime x t. For the time being, for the sake of simplicity, I am going to drop the arrow operators from x, and we would presume that wherever we write x, that represents the 3-dimensional coordinates of a point. Now, how did we define our average operator? This phi bar x, this was defined as a limit t tending to infinity 0 to t phi x t dt 1 over capital T. So, we would say this wherever we use over bar, that represents this particular Reynolds averaging operator or Reynolds averaging procedure. Now, let us apply this procedure to our decomposition. So, let us apply this integration process or this averaging process on both the sides of equation 1. So, apply this averaging process to both sides of equation 1, then what we get? On the left hand side, we will get phi bar. In fact, that is what we will get after averaging. If we average this phi bar x t, we get simply phi bar. What would be the time average of an average quantity? Remember, this phi bar does not depend on time. So, if we want to take its average over a long time interval, it will remain phi bar. So, the first term on the right hand side, what we get, that remains such phi bar x, and the next term which we had was this phi prime bar. X comma t. So, what do we get from here? It is obvious enough that average of the fluctuations, that is equal to 0. So, this is first rule of our Reynolds averaging procedure. Now, what will happen if you want? Let us have a look at the next few rules in this algebraic process. This we have already clarified, that average of the average, that will remain phi bar. The next thing is differentiation and integration. They commute with this averaging process. A differentiation also represents a linear operation. So, that is what we say, that differentiation and averaging process, they commute. That is why we can say del phi by del s over bar, that is average of del phi by del s is same as the derivative of say del by del s of phi bar. Similarly, if you have had an integral phi ds, s average is same as the average of phi bar ds. So, in nutshell, what it means is our two linear operations, for instance in this case the differentiation and averaging, they commute. Similarly, integration and averaging, they also commute. Similar, if we had the sum of two quantities, two fluctuating quantities phi and psi, the sum of the two, that would represent the third quantity which is fluctuating with time. So, how do we get the average of that quantity? That is simply given by the average of two quantities. So, phi plus psi bar is equal to phi bar plus psi bar. So, now let us verify these terms, and next But when we have a product, now remember this product is no more a linear operation. So, product of phi into psi, its average would be given by these two terms, that is phi bar plus phi bar into psi bar plus average of the product of the fluctuating components phi prime and psi prime. Suppose we want to find out the average of phi plus psi. How do we work it out? If we by definition this is limit capital T tending to 0 1 by capital T integral 0 to T phi x t plus psi x t dt. By the basic rule of algebra, we know this integral can now be broken into two parts, integral of the first function plus integral of the second function. So, we get within bracket 0 to capital T phi x t dt plus 0 to capital T psi x t dt. Limit again, the limit of two quantities, a sum of two quantities, that is equal to the limit of each individual quantity. So, limit capital T tending to 0 1 by capital T 0 to capital T phi x t dt plus limit capital T tending to 0 0 to capital T psi x t dt. And you can easily recognize these two limits, they are nothing but the respective averages phi bar plus psi bar. Now, next let us have a look at what happens if we had, if you want to find out the average of the product of the two functions. So, we want to find out what will happen to phi to psi. Now, let us use our Reynolds decomposition. So, phi can be expressed in terms of phi bar plus phi prime, and psi can be expressed as psi bar plus psi prime, and we want to apply this our averaging operator to both of it. Now, let us multiply and open this product. So, we get phi bar psi bar plus phi bar psi prime plus psi bar phi prime plus phi prime psi prime. So, here we have got we want to take average of these quantities which are being separated by the addition operator. So, this overall summation can be now broken by the average of the separate quantities. So, we get this phi bar psi bar average plus phi bar psi prime average plus psi bar phi prime average plus phi prime psi prime average. Now, remember the way we have defined this average of phi bar and average of psi bar, this independent of the time. So, this would essentially be the product of phi bar psi bar. Similarly, from the next term of phi bar comes out and we get the psi prime bar plus psi bar and phi prime bar plus phi bar psi prime whole over bar. We have just learnt earlier that the average of the fluctuations, that is 0. So, these terms which contain the average of fluctuating terms only, these become 0. So, we get in the average of the product of two functions phi psi, that is given as the product of the individual averages plus average of the product of fluctuations. So, look carefully, the average of the fluctuations, product of fluctuations, that will not be 0, that will depend on how these two quantities are correlated. Now, we can use these rules and apply these rules to our Navier-Stokes equations to obtain the so called Reynolds averaged Navier-Stokes equations. So, the summary of the equations on the slide, and now let us see how do we actually obtain these equations. So, first one we would like to find out, we would apply Reynolds averaging procedure to our continuity equation. So, Reynolds averaged Navier-Stokes equations and for the time being we will discuss the case of incompressible flows for which density is constant. There is a slight difference procedure for obtaining this Reynolds averaging process, which is referred to Fourier averaging for compressible flows or variable density flows. So, that is something which I would leave you to explore from the literature. For the time being, let us focus on the continuity equation for our incompressible flows. This will be a del rho by del t term that vanishes. So, we get del over del xi this is equal to 0, or Vi is our velocity vector. So, apply averaging process to it. So, apply Reynolds averaging to the above equation. Now, remember the rule which we had learnt earlier, that differentiation and averaging process they commute. So, this will be simply del by del xi of Vi bar. So, thus our time averaged continuity equation becomes del Vi bar over del xi is equal to 0. Or sometimes in our calculations we keep density together, density is a constant, so that it does not really matter if you want to put it inside the brackets. So, del Vi bar divided by xi. So, these are two forms which are frequently used in numerical simulations. Both of them are basically identical for incompressible flows. Next, let us work on our Navier-Stokes equations, and we will have a look at each term separately and find out its average. So, Navier-Stokes equations were given by del over del t of rho Vi plus del over del xj of rho Vi Vj is equal to minus del p over del xi plus del over del xj of tau ij plus rho Bi. This was our time dependent Navier-Stokes equation. So, now let us apply the averaging process to each term. So, apply Reynolds averaging to each term. The first term contains a time derivative. So, del over del T of rho V I, we want to find out the average of it. Remember again that averaging and differentiation, they commute. So, del by del T of rho V I average. Rho was basically a constant for incompressible flows. We can also write this as del over del T of rho V I bar. So, this is our first term. The tricky part is the next term, which is convective term, del over del x j of rho V I V j over bar. So, averaging process that will commute with our differentiation operator. So, this is del by del x j of rho V I V j over bar. Now, remember what we have learned earlier, we call that formula, recall that the product of phi and psi, their average is given by the product of phi bar psi bar plus phi prime into psi prime average, that is average of the product of fluctuating components. So, use it in equation 3. So, therefore, equation 3 becomes del over del x j of rho V I V j over bar is equal to del over del x j of rho V I bar V j bar plus del over del x j of rho V I prime V j prime over bar. Okay. Similarly, the two terms on the right hand side, they are linear operators. So, we can straightway apply the averaging process. Bi is the source term or what we call body force term, which would actually not depend on the turbulence, it will be a fixed quantity. So, thus Reynolds averaged Navier-Stokes equation becomes del by del T of rho V I plus del over del x j of rho V I bar V j bar plus del over del x j of rho V I prime V j prime whole over bar is equal to minus del P bar over del x I plus del over del x j of tau I j bar plus rho B I. Now, what we normally do is transfer this term which involves the fluctuations to the right hand side and club it with our stress term. So, rearrange del by del T of rho V I bar plus del over del x j of rho V I bar V j bar is equal to minus del P bar over del x I plus del tau I j bar del x j minus del rho V I bar V j bar del x j plus rho B I. So, this is what is referred to as Reynolds averaged Navier-Stokes equation. On the left hand side you see this equation basically is a transport equation for time averaged or Reynolds averaged velocity components Vi bar. So, we have the first term is our temporal term, this will vanish if our flow were statistically steady, and next term is a convective term in terms of the averaged velocity components Vi bar and Vj bar. The first term on right hand side, that is a gradient of time or a Reynolds averaged pressure field. The next term, this del tau ij bar over del xj bar, that is for in terms of our Reynolds averaged velocity components, that is how we would compute tau ij bar. But we have got additional term here, that is Vi prime Vj prime over bar. We do not know what are these components, these are unknown components, and in fact it represents a second order tensor which will have 9 components. So, the averaging process has introduced an unknown tensor quantity which must be modeled, and that is the essence of the Reynolds stress models, which must be used to ensure what we call the closure of these equations. Okay, similarly, if we had a scalar transport equation, we can again apply our averaging procedure. The left hand side remains in the form very similar to our normal equation, del by del T of rho phi bar plus del over del xj of rho Vj bar phi bar is equal to del over del xj gamma of del rho phi over del xj plus qj bar. This is an additional term. We normally use the symbol tau ij subscript r, sorry, superscript r, and we call this as Reynolds stress, which is defined by minus of rho Vi prime Vj prime. So, this is fluctuating components, they give rise to a stress like term. That is the reason why we call them Reynolds stresses. Similarly, this is a turbulent flux, which is in terms of the fluctuating components of velocity would lead to additional scalar transport, and that is the reason why it is referred to as turbulence flux. Let us have a look at the physical significance of these Reynolds stress terms. So, these stresses, the way we saw, they involve a time correlation, that is why we had this Vi prime Vj prime over bar, that is a time correlation of the fluctuating components of velocity. So, the main consequence of these velocity fluctuations of turbulence is to enhance shear stresses and thus the transport of momentum within the flow. So, the Reynolds stress tensor contains components that are velocity fluctuation correlations, and you can verify this is symmetric tensor and has 9 components. So, we will have basically 6 unknown components for this symmetric stress tensor, and those have to be somehow modeled in terms of time Reynolds averaged velocity field. So, this is what majority of turbulence models attempt to do to ensure closure of Reynolds averaged Navier-Stokes equations. Similarly, the turbulent fluxes, they arise from the convective transport due to turbulent fluctuations, the fluctuations of the velocity field as well as fluctuations in the scalar component. Okay. So, when this equation is time averaged, the influence of fluctuations over averaging time period is included via these additional flux terms, which represent enhanced heat transfer or enhanced mass transport, and they are result of the Reynolds averaging applied to our conservation equation, and their sole purpose is to incorporate the effect of turbulence in enhancement of the transport of the respective quantities. Now, let us have a look at some of what we call RANS turbulence model, Reynolds averaged Navier-Stokes turbulence models, and we can classify these turbulence models broadly into 2 categories. The first one is what we call eddy viscosity models, and these models, they employ what we call eddy viscosity assumption based on Bouguin proposition. The proposition of Bouguin was that we can incorporate these enhanced effects coming from the fluctuating components via an additional or enhanced viscosity, and since that viscosity is basically caused by the eddies or what we call fluctuating components of the velocity field. So, that is why this term eddy viscosity is used here. And the other model is what we call Reynolds stress for the velocity field, that is for Navier-Stokes equations, and Reynolds flux model for our scalar transport equation. So, now these employ additional transport equations for Reynolds stress tensor and turbulence flux. Now let us have a brief look at few other categorization. These turbulence models can also be categorized based on the number of additional transport equations which we must solve. For instance, if you are solving a time dependent problem or incompressible flow problem, we have to solve continuity equation and 3 momentum equations. So, we have to solve 4 coupled partial differential equations in laminar flow. For turbulent flow, to take care of these fluctuating components or what we call Reynolds stress components, we have to use additional number of partial differential equations. So, how many number of additional transport equations which we need to employ, a categorization of RANS models can be based on that as well. So, the number of additional PDs which we must need to enforce the closure, the simplest one would be we do not use any additional partial differential equation. We somehow get an estimate of this eddy viscosity based on the time averaged solution for the velocity field, and this popularly referred to as Prandtl's mixing length model. And since there are no equations, no additional PDs are involved, this is referred to as zero equation model. Then we can have one additional PD, for instance one model known as Spallard-Alamaris model that implies one additional partial differential equation to compute the eddy viscosity. So, that is why it is referred to as one equation model. But the most popular in industry are what we call 2 equation models, for example K epsilon model, K omega model or algebraic stress models, which imply 2 additional transport equations, 2 additional partial differential equations. For instance, K epsilon model, we will have one equation for this kinetic energy K and one equation for the dissipation term epsilon. And if you go for Reynolds stress model, we have basically 7 equations. So, this Reynolds stress model is referred to as 7 equation model. So, you can just realize that if you want to solve an incompressible flow problem, we had 4 equations or 4 PDEs, one corresponding continuity equation and 3 for momentum equations, and to incorporate these Reynolds stresses we need to solve for 7 additional equations, which will lead to a tremendous computational burden. So, that is why these Reynolds stress models, they are used rather infrequently in industrial CFD simulations. And there are some more things which we must remember, that all these models, they involve empirical numerical constants. These models they are called models, they have not been arrived from rigorous first principles of continuum mechanics. Majority of them are based on the extensive experimental data, okay, and empirical numerical constants have been obtained based on the validation of an assumed model with experimental data. And these constants which we get from the experimental data, of course those will depend on the circumstances or the problems for which the experiments were performed. So, that is why these constants are not universal, in the sense that suggested values may not yield correct results for all turbulent flows, and hence the care must be exercised in the choice of the model constants. We might have one set of model constants, let us say in one type of flow, and for a different type of flow we have to go for either a different model, or we have to fine tune, or we might have to change these model constants. And the fine tuning is typically achieved using 2 means, that is we can perform extensive controlled experiments, that is one. And another way is to use direct numerical simulation on a very small computational domain, perform very fine grid direct numerical simulation, and that can be used to fine tune the model constants in the RANS turbulence models. So, both of these approaches, these are very active areas of current research in turbulent flows, that is perform direct numerical simulation on certain set of geometries, certain flow situations, and perform a RANS simulation for the same problem, for similar type of a problem which involves similar physics, and then try to fine tune the model constant used in RANS model, so that the RANS model gives the average quantities which are fairly close to what we would obtain from direct numerical simulations. So, still it is a very active open area of research. Now, we will have a look at Boolean proposition which we just referred to. Now, this Boolean proposition is based on one simple observation which Boolean had, that look, if we had a simple laminar flow, our stresses, viscous stresses, they are proportional to what? They are related to velocity gradients. So, they are proportional to velocity gradients, or what we call a strain rate tensor. And normally for Newtonian fluids, we say the deviatory components, they are directly proportional to what? Viscosity times the strain rate tensor. So, can we do the same thing? So, a tremendous experimental evidence and theoretical evidence to suggest that the rate of mixing due to turbulence, or the turbulent eddies themselves, they depend on the velocity gradients in the flow. So, based on those experimental and theoretical observations, Boolean proposed that even Reynolds stresses, they should be proportional to the mean velocity gradients, especially the deviatoric Reynolds stress, it is proportional to the mean rate of strain. So, in terms of the symbols which we have introduced, tau ijr, that is what is our Reynolds stress tensor, which is equal to minus rho vi prime vj prime over bar. This can be represented in terms of mu t multiplied by velocity gradient or strain rate tensor. So, mu t times del vi bar over del xj plus del vj bar over del xi minus 2 by 3 rho k delta ij. So, the first term on the right hand side, you can clearly say this is mean velocity gradient, and the constant multiplier which you have taken, in fact this is not a constant, this would depend on the position in the flow field. So, it will vary from point to point in the flow field, and this particular symbol, so we have used the same symbol which we use for viscosity. So, this is referred to as mu t is called dynamic turbulent or eddy viscosity. The term eddy is often used to correlate or to put it formally that look, these stresses arise because of the different eddies which are there in the turbulent flows. So, that is why this mu t is called dynamic turbulent or eddy viscosity, and a small k which we have used in this relationship, that is what is referred to as turbulent kinetic energy. That is to say, we obtain mu prime square over bar plus v prime square over bar plus w prime square over bar divided by 2. This gives us turbulent kinetic energy per unit mass. So, this is the Boolean proposition which is the basis of eddy viscosity based turbulence models. Similarly, the same concept can also be applied to the diffusion of a scalar quantity. That is to say, we can say that turbulent fluxes will also be proportional to the gradients of the scalar quantity. So, we can say this qj r which was defined as minus rho v j prime phi prime over bar, this is equal to gamma subscript capital T del phi bar over del xj. So, this del phi bar over del xj, this is the gradient of the mean value of the scalar field phi, and this gamma subscript T, this is called turbulent or eddy diffusivity. And remember, this gamma T or mu T which we have introduced earlier, these are not material properties. Okay, these depend on the flow and they would vary from point to point. So, we have to obtain estimates of these quantities at each point in our numerical simulation, and that is precisely what turbulence models attempt to do. So, this we will take up few of the popular turbulence models in the next lecture. For the time being, we will have just a brief look at their names. So, eddy viscosity based RANS models, we will have a brief look at mixing length model, we will briefly look at Spalart-Alameras model, then standard K epsilon model. For the improved models like K epsilon RNG model or realizable K epsilon model or K omega model, I would refer you to appropriate references or rather a textbook. So, today we stop here In the next lecture we would have a bit more detailed look at few of these turbulence models and our Reynolds stress model, and thereafter we will start off with large eddy simulation.